Welcome to day 13 of my AVR Advent Calendar. In this series of videos I show you in 24 days how to program the AVR 8-bit microcontrollers. Today I don't have a paper bag because we will still be using this variable resistor and we will continue talking about analog inputs on our AVR microcontroller. And today we will take a look at the analog digital converter of our AVR microcontroller. So basically, an analog digital converter, or short ADC, takes an analog input and converts it to a digital value which can be processed by the microcontroller. And if we take a look at the pinout of our AppMega microcontroller, we can see we have 6 ADC pins here, and these pins can be used as analog inputs. And something else to mention is, down here we have 2 analog power supply pins. We have the analog power supply and the analog reference pin here. And if we want to use the ADC, we have to use these 2 pins too. But we will talk about this later when I go into my connection diagram. Okay, so let's take a look at the registers we need for programming this ADC. The first important register is this ADC multiplexer selection register. So you have seen we have up to 6 ADC pins, but we can only use 1 at a conversion. And here over this, for a multiplexer bits, we can set the desired value. For example, I want to use ADC number 5, and so I have to write a 5 into these 4 bits here. Then up here, the most significant bits up here are for the voltage reference selection. So if we set them to 0, we will use the reference voltage applied on the ARF pin. But we could use, for example, if we set these 2 bits to 3, we could use an internal 1.1 voltage reference 2, but I won't use it here. Then the another important bit is this ADC control and status register A. So bit 7 is for enabling the ADC. Over bit 6 we can start a conversion. So if we write a 1 to ADC start conversion here, it will start a single conversion. And when the conversion is done, it will reset this bit back to 0. Then here we could set an automatical trigger, so I will use a free running ADC, so I will have to set this bit every time I want to have a new conversion, but you can use a timer, for example, for auto triggering a new conversion, but we won't use this. The next 2 bits are interrupt bits, so this will enable an interrupt when a conversion is done, and this is a flag you can test and to see if a conversion is done. And the last 3 bits here are for a clock prescaler. Because you have to know an ADC uses a clock for a conversion, or it needs a clock for doing a conversion, and here we can set a prescaler. So in this table we can see, depending on what value, which prescaler we will use. The thing is, here I have a 60 megahertz internal, or I'm using a 60 megahertz clock, and if I would set the prescaler bits to 0, we would have to divide the clock by 2, so we would have an 8 megahertz ADC clock. And this is a little bit too fast for the ADC. It doesn't work well with this division factor, so I will use this prescaler of 32. But of course, as bigger the prescaler, as longer it takes for a single conversion. But here in our application, it doesn't matter. Then the next important register is the ADC data register. So in this register we can find the digital value of our analog input. And here you can see our ADC has 10 bits. Yeah. And there are some other registers, for example the analog digital converter control and status register B. And here I've already told you could use automatical triggers here, and over these 3 bits you can select the trigger method. So here we see it, we will use this free running mode, which is the default value, but for example you could also use timer 0 or timer 1 for automatical triggering a new conversion. And this ACME is just for the analog comparator, but I won't use it, so I will set this to 0. Okay, with this knowledge, let's jump to the wiring diagram. So here it is. So basically you can see I'm applying my 5 volts to the AVCC and the ARF pin, and I'm connecting this extra ground pin here. And here my variable resistor is connected to ADC5. And that's everything. And I'm using this USB to UART converter to write my analog or to write out the measured value to my PC over UART. Okay, so with this knowledge we can start programming. So let me navigate into my AVR Advanced Calendars folder here, and you can see I've already created a new folder called 13ADC to save us a little bit of time. And here, let me run a clean first. We have our main file and a make file to build our source here. So let me open up main.c. So this is basically the example we have used for the UART. I just have added some functions here. So this function print will send a zero terminated string over UART, and this float to string function will convert a float to a string, because I will calculate the voltage level as a float from my ADC pin, and then I will convert it to a string and send it over UART with this print function up here. Okay, and here in the main function there is just everything we need for setting up the UART. Okay, so now let's add our code for the ADC. First we have to initialize the ADC. With the ADC multiplexer I will set to 5 to select ADC pin 5. Then in the status and control register A, I will set the enable ADC bit, and I will set my prescaler to 5, and 5 means 32. Okay, and so much for initting the ADC. Now let's start a conversion. So for starting a conversion, I have to write to the status and control register A again, and this time I will set the start conversion bit here, and this will start a conversion. And I know if the conversion is done by checking for the AD start conversion bit here, and when this bit is set to 0, the conversion is done. So here, waiting for conversion to be done. Okay, and now I need some variables. So first I will need a text or a string. I will call buff here for storing the converted value. Then I will need an unsigned integer value, which I will call raw temp or just raw. And then I will need a float. I will call voltage, and this pin or this contains the voltage value on my analog input here. Okay, so now I will set raw to ADC. Here I have the result, and now I will calculate the voltage. So the maximum voltage is 5 watts, and I will multiply this with my raw value here, and then I will divide it by 1 shifted by 10, because this is the maximum resolution and this should be 1024 here. Then I will use float to string here to convert my value. So I will convert the voltage, and I want to save it in my buffer variable, and then I will do some prints over UART. So voltage or analog input print, then I will send my buffer, and then I will print voltage, and I will start a new line here. Okay, and then let's add a small delay. So I want to wait 1 second between two conversions. Or let's do half a second. Okay, this should be it. Let me compile it. Okay, yeah, I have an error here. ADC, yeah, status and control register A. Status and control register A. Yeah. Okay, once again I failed. Let me copy this here. Okay, now it should be okay. Yes. So let me flash this program by using the AVR dude. So I will write to my flash, and I want to write the file adc.hex. So let me flash this. Okay, now it's done, and you can see here it's sending bytes. So let's see what it sends. Therefore, I will use screen as my serial terminal. Dev tty USB 0, and my baud rate is 4800. Yeah, this is the analog voltage, and if I take my screwdriver and change it, yeah, you can see the value is changing too. So now it should be 5, yeah, and now it should be 0. Okay, cool. So this is how to use the ADC. I hope you've enjoyed the video and learned something, and I also hope I will see you in my next video tomorrow. Bye!